Hey guys, it's Ryan, and today we're going to talk about tonicity and osmolarity. So here we have a series of tubes, and we're going to fill each one up with different amounts of water and solute, and see the direction that molecules will travel based on concentration gradients. So you'll notice that each tube has a white line down the center, separating the left and right sides, and this will be the plasma membrane. So certain molecules will be able to pass through while others will not, hence it being semi-permeable. So let's go ahead and fill this up with water, and the levels will be equal because the membrane is permeable to water. Now let's go ahead and add some solute on the left side and a little bit less of that same solute on the right side. So without knowing anything about the character of this solute, we can say that the left side of the tube is hyperosmotic to the right side, just because there's more total solute. It doesn't matter if the solute can penetrate the membrane or not. Just the fact that there's more stuff on the left side means that it's hyperosmotic. So knowing this, we know that there's a concentration gradient between the left and the right sides with respect to water, so we'd expect water to move to the right. But let's say that this solute is penetrating, so it can penetrate this membrane. So now we have another concentration gradient to consider, that there's more of the solute on the left than the right. So in order to reach balance, because everything in nature wants to reach balance, this solute is going to want to travel across the membrane to the right side. So now if we drew the after image after equilibrium, the solute is going to end up similarly spaced on both sides to reach equilibrium. And then whatever volume that these solute particles were taking up on the left side, they're just simply filled up with water, so that the water levels are equal and the solute concentrations are equal. And this would be an isoosmotic solution, or rather they'd be isoosmotic to each other. And that's an important point to make, because when we talk about osmolarity and tonicity, you always have to say relative to something else. You can't just say a solution's hypertonic and that's it. You have to say it's hypertonic to something else, or hypoosmotic to something else. Alright, so if we go to this tube, we're going to fill up again with water, but this time we're going to use a non-penetrating solute. So we'll say that we have, again, more on the left and a little bit less on the right. So now this time, the solute would like to travel across the membrane to even out the concentrations, but it can't. So now water is the only thing that can move. So this time we're just going to have osmosis of water across the membrane to the left. And in this way, it's going to evenly space out the solutes as before, but the water concentrations, or rather the water volumes, are going to be different. Because in order for the water to come over, this water level is going to have to rise. We can also say that this solution on the left here is hypertonic, because we're talking about non-penetrating solute this time. We can also say that it's hyperosmotic, but hypertonic is a little bit more specific and detailed to this specific case. Now, another interesting thing to notice here is that there's sort of a pressure, an osmotic pressure that's established in this situation, where water wants to move left and eventually push up on the left side. So if you can imagine us putting a rubber stopper over the top of this left side of the tube and pushing down, we could essentially stop the osmotic pressure and keep the concentrations where they are. This would be an example of applying positive pressure. Or we could use a straw, throw a straw on the right side, and suck air out. In this way, again, contradict the osmotic pressure going to the left. This would be an example of applying negative pressure. And in each of these scenarios, we could actually stop the movement of water and keep everything where it is. Okay, so now that we went over all of this, let's look at a question. So if a small amount of urea, which is a penetrating solute, were added to an isoosmotic saline solution that contains cells, what would be the result at equilibrium? So go ahead and pause the video, work through the problem, and then we'll go over it together. Alright, so I hope you did well. Let's see what happens. So if we have a solution here, and I'm going to draw a cell because it says it contains cells, and it also says that it's isoosmotic. So the solution must be isoosmotic to something else. So we're going to assume that it's talking about the cells that are in the solution. So here's our solution, and the solute is evenly spaced out between the cells and the solution itself. Now, if we were adding in urea solute, that urea, let's use a yellow, is a penetrating solute. So that's something that we need to consider when solving this problem. So let's say we add in this small amount of urea, and then let's think what would happen right after we add that. Now let's ask the question, what happened to the solution? Well, now it's hyperosmotic to the cell. It's not hypertonic because this solution is penetrating, but it is hyperosmotic, which means that water will want to move out of the cell in order to even out this concentration. But urea is a penetrating solute, so the urea is going to want to enter the cell because there's another concentration gradient formed. There's more urea outside the cell than inside. So this is going to easily diffuse through the membrane into the cell. And the question is asking at equilibrium. So this means that after all the concentration gradients have been evened out, if possible, what would be the result? So if I draw it again down here, the orange solutes are already evenly spaced, and now the yellow urea will soon join it because it can easily pass over the membrane. So now both concentrations are evenly spaced out. So that means that water doesn't actually have to go anywhere. Maybe some leaked out of the cell originally because the solution was hyperosmotic, but at the end of the day, at equilibrium, the solution is again isoosmotic, and so water didn't have to leave the cell or enter the cell. So this would be the result at equilibrium. The cell size would not change. Alright, so I hope you found this video helpful, and I'll see you all next time.